Hello students, in this video we'll begin our discussion of Lagrange interpolation. If I'm given n plus 1 points, x0, y0, xn, yn points in the plane, can we find a polynomial p n of x, which is a0 plus a1 x plus an x to the n, that interpolates these points, that interpolates these points. In other words, I want p n of xi to be equal to yi for I between 0 and n, right? And of course, we know the answer to this comes from linear algebra, right? So I can write this as a linear algebra problem. I could say that a0 plus a1 x0 plus a2 x0 squared plus an x0 to the n. I need that to be y0 all the way down to a0 plus a1 xn plus a2 xn squared plus an xnn is equal to yn. I need this system of equations to have a solution, right? And that corresponds to the coefficient matrix having a non-zero determinant, right? So this has a solution, so let's call this over here star. So star is solvable if and only if this determinant of 1, 1, 1 over here, 1, 1, 1, 1, and then then x0, xn, x0 to the n, xn to the n is non-zero, okay? And this, of course, is our Vandermonde matrix. This is a Vandermonde matrix. And I know what the determinant of that is. The determinant of this is actually just equal to the what? Is equal to the product over I less than j, not equal to j, of xj minus xi, right? So in other words, the two of these x's cannot be equal to each other, otherwise the determinant will be equal to 0. So that exactly tells us, this criterion tells us what the solution, when the solution is possible, right? And so we can actually figure out what the actual polynomial is going to be, right? So the actual polynomial, Pn of x in this situation, is going to be the sum, j goes from 0 up to n, of yj like that, and then the function L of x over L prime of xj times x minus xj like that, where here L of x is just this product function. It's just going to be x minus x0 all the way down to x minus xn like that, right? And of course, you might say, well, what happens when we plug in xj into this formula over here? Well, there we have a 0 in the denominator, right? So I'll have to use L'Hopital's rule. So if I use L'Hopital's rule on this portion over here, so if we plug in xj into this polynomial over here, so Pn of xj is equal to just the limit as x goes to xj of that expression over there, the sum. So in other words, if I plug in xj to a term over in this, to this expression, we're going to have just what term over here? Just the term that's going to survive is just going to be the xj term. And so we're going to have just the limits. We're going to have a yj. It's going to be yj over L prime of xj. And then the limit as x approaches xj of L of x over x minus xj, right? And of course, L of xj is equal to 0 because it's determined this product over here, right? So in other words, L of xj is equal to 0 for j between 0 and n, like that, right? And so this will just be, by L'Hopital's rule, this is just going to be yj over L prime of xj, and then L prime of xj, which is yj, and this comes from L'Hopital's rule. Right? Okay, sort of a trivial version of L'Hopital's rule because it's a removable singularity, right? But it just works, right? And so now what I can do is I can use this to extend to try to find an approximation of a continuous function by a polynomial like this, right? And so if I'm given n plus 1 points, distinct points now, x0, x1, xn, belonging to an interval AB, then what we can do is we can form Pn of x, which is equal to what? Which is equal to the sum. J goes from 0 up to n of what? Of just f of xj, of those points, times L of x over L prime of xj, and then x minus xj like that, right? So in other words, this polynomial has the same value as a continuous function at those points, right? So in other words, p of xj, Pn of xj is equal to f of xj. In other words, this polynomial agrees with that function at those n plus 1 points over here, right? And so now what I'm going to do is I'm going to add on one more point to this and get an inequality over here. So let's do this now. So now pick x in AB, not one of these roots, x0 through xn. And then consider this function over here, and consider an auxiliary function, g of t, which is going to be f of t, and then minus Pn of t, okay? And then I'm going to look at this thing over here. Then I'm going to put a plus f of x minus Pn of x over L of x, and then L of t, like that, okay? All right, and so now what can we say over here? So now, what do I know about g, for example, of, so I know if I plug in any of these x0 through xn to L, they'll vanish, and I know that f agrees with that polynomial at those points over here, so g vanishes, and not only at x, and it also will vanish at x, right? Because if I plug in x over here, it will vanish. So g vanishes at x, x0, x1 through xn, like that, okay? So in other words, it has a total of n plus 2 zeros, right? So g has n plus 2 zeros, and they're distinct zeros, right? So in other words, the zeros over here line up like this. So in other words, here's A, and here's B, and then there's a whole bunch of zeros, okay? 0, 0, 0, 0, 0, 0, 0, 0, 0. Now, between each of those zeros, what can I say? Between each of those zeros, there's a point where the derivative is equal to 0, right? And between each of the points where the derivative is 0, there's going to be a point at which the second derivative is 0. So in other words, it has n plus 2 zeros, then g prime has n plus 1 zeros that are interlacing. G double prime has n zeros, and finally, gn plus 1 has at least 1 zero, right? So gn plus 1 has a root, okay? In other words, gn plus 1 xc is equal to 0 for some value of xc, right? Now, of course, what is n minus 1 derivatives of that? It's going to be n minus 1 derivatives of the function f, right? So this is equal to what? This is equal to what we have over here. It's going to be f n plus 1 xc. And then this quantity over here, and let's make sure I have the right sign over here. So do I have the right sign? Actually, I need to turn this into a negative sign. So one slight modification will help me get what I want. So let's just change that to a negative sign, and now it will work out, right? Because now when I plug in x over here, now I'm going to have f of x, so it will work now. So in other words, this function g will have a root at x if that was a minus sign. So change that to a minus sign in your notes. Excellent. And so now, what will this be? This is going to be minus f of x minus Pn of x over L of x. And then if I do n plus 1 derivatives of L of t, that's a polynomial degree. N plus 1, so I'm just getting n plus 1 factorial, n plus 1 factorial. And so what this allows me to conclude is that the difference, so what we have now from this is that we have that f, the absolute difference between f of x, the continuous function, and this polynomial interpolant of it will be what? Will be no more than 1 over n plus 1 factorial, the maximum of the n plus first derivative, n plus 1 derivatives in L infinity, and then times this function absolute value of L of x. Okay? So we now have this inequality over here, which says that if you do this sort of Lagrange interpolant, so this of course is called the Lagrange interpolating polynomial. Okay? And for the Lagrange interpolating polynomial with a continuous function that has n plus 1 derivatives, or just say c infinity, the absolute difference between the function f and that polynomial interpolant is no more than 1 over n factorial, the largest that the n plus first derivative can be on that interval, and then times the what? Times that interpolating function over here, this L of x, right? And so what this tells me is if I wish to minimize the difference between the function and this interpolating polynomial, what I need to do is I need to find the right sort of spacing of these points in the interval, in which will make this L of x as small as possible, and that's where we're going to introduce our study of Chebyshev polynomials, which help us find a way to sort of equally space these points x0 through xn to give me the sharpest way to approximate a function by a polynomial on a compact set. Thank you very much.